Buenas tardes. Es para mí un verdadero placer darles la bienvenida en nombre del Gobierno de Aragón a esta conferencia del profesor Alain, Premio Nobel de Física de 2022, y hacerlo además aquí en Teruel, en el marco de las actividades científicas y divulgativas en torno al eclipse. Esta relevante conferencia se ha organizado conjuntamente por el Centro de Estudios de Física del Cosmos de Aragón, la Dirección General de Ciencia e Investigación del Gobierno de Aragón y el Ayuntamiento de Teruel, además de la colaboración de Caja Rural de Teruel. A todos ellos, gracias. Bueno, yo primero tenía que haberme presentado, soy Pilar Gallán, soy la directora de Ciencia e Investigación del Gobierno de Aragón y por eso les estoy dando la bienvenida. Y quiero destacar algo que resulta especialmente relevante esta tarde. Tenemos la sala llena. Una sala llena para escuchar hablar de física cuántica, y eso por sí misma ya es una magnífica noticia. Y demuestra que la ciencia interesa y que existe curiosidad y que cuando somos capaces de acercar el conocimiento a la ciudadanía, la sociedad responde. Y además hoy volvemos a vivir aquí en Teruel un acontecimiento verdaderamente excepcional. Es la primera vez que un premio Nobel nos visita en Teruel. Y lo hace en unas fechas en las que la ciencia está adquiriendo un protagonismo extraordinario en nuestra provincia. Ayer mirábamos todos al cielo y hoy vamos a intentar comprender un poco mejor aquello de lo que está hecho. Ayer miles de personas tuvimos la oportunidad de vivir un acontecimiento extraordinario, un eclipse que convirtió a Aragón y de una manera muy especial a Teruel y a Javalambre en lugar de encuentro entre la ciudadanía, la ciencia y el cosmos. Y creo que difícilmente podríamos encontrar una mejor continuación a esa experiencia que escuchar hoy a uno de los grandes científicos de nuestro tiempo hablarnos de otra revolución que ha cambiado profundamente nuestra manera de comprender la naturaleza, la revolución cuántica. Son tecnologías que probablemente tendrán un enorme impacto en nuestra economía, nuestra industria y nuestra sociedad durante las próximas décadas. Y precisamente por eso resulta importante que la ciencia no permanezca encerrada en los laboratorios. La ciencia necesita investigación, pero también necesita divulgación. Necesita investigadores capaces de ampliar las fronteras del conocimiento, pero necesita también ciudadanos que comprendan por qué investigar es importante y por qué una sociedad que apuesta por la ciencia está apostando por su propio futuro. Ese es también uno de nuestros grandes objetivos desde el Gobierno de Aragón. Queremos que Aragón sea reconocida por su patrimonio, por su territorio, por su calidad de vida, pero por supuesto también queremos que lo sea por su capacidad para generar conocimiento, atraer talento y participar en las grandes preguntas científicas de nuestro tiempo. Y Teruel y Javalambre son un magnífico ejemplo de ello. Contamos aquí con una infraestructura científica singular, con proyección internacional, pero sobre todo con una comunidad científica capaz de demostrar que la excelencia investigadora no depende del tamaño del territorio ni de su distancia respecto a los grandes centros internacionales. La ciencia de primer nivel también se hace en Aragón y se hace desde Teruel. Por eso, actividades como esta tienen un valor añadido. Acercan la investigación de excelencia a la sociedad y permiten que durante unas horas científicos y ciudadanos compartamos el mismo espacio y, sobre todo, las mismas preguntas. Profesor Aspect, bienvenido a Aragón y bienvenida a Teruel. Professor, welcome to Aragon and especially to Teruel. Thanks for your talk. Es para nosotros un auténtico privilegio contar hoy con su presencia. Esta tarde tendremos la oportunidad de conocer mejor qué significa esa segunda revolución cuántica, qué aplicaciones están empezando a surgir y qué oportunidades puede generar para nuestros investigadores, nuestras universidades, nuestros centros tecnológicos y también nuestras empresas, ¿por qué no? Pero me gustaría que además de conocimiento nos lleváramos de esta conferencia a otra cosa, curiosidad. Porque antes de cualquier descubrimiento científico hubo siempre alguien que se atrevió a hacerse una pregunta. Espero que Alain nos cuente cuál fue la suya. Y ayer un eclipse nos hizo a todos levantar la mirada al cielo para intentar comprender mejor el universo. Y hoy, de la mano del profesor Aspect, vamos a dirigir esa mirada hacia lo más pequeño, hacia ese mundo extraordinario en el que las leyes de la naturaleza desafían muchas de nuestras certezas. Y quizás sea esa una de las grandes enseñanzas de la ciencia, que cuanto más sabemos, más preguntas somos capaces de hacernos. En nombre del Gobierno de Aragón, gracias al profesor Aspet por esta invitación, gracias al Cefca por su extraordinario trabajo científico y su compromiso con la divulgación, gracias a todas las instituciones que han hecho posible este encuentro y, por supuesto, gracias a ustedes por acompañarnos. Les dejo ahora con el profesor Cenarro, el director del Cefca, que nos va a presentar un poquito más en detalle al profesor Aspet. Gracias y que disfruten.
Muchas gracias, directora general. Voy a presentar muy brevemente el currículum del profesor Alain. La verdad es que como no es muy habitual presentar a un premio Nobel, pues he preferido traerlo apuntado para no dejarme el más relevante. Simplemente comentar que Alain Aspect, el profesor Alain Aspect es francés, es uno de los físicos más influyentes de nuestro tiempo. Licenciado en Física y diplomado en Óptica, desarrolló su carrera investigadora en el Instituto de Óptica de la Universidad de París-Saclay, donde llevó a cabo los experimentos que demostraron por primera vez y de forma concluyente la violación de las desigualdades de Bell, cerrando así un debate de más de 50 años iniciado por Albert Einstein sobre la naturaleza de la mecánica cuántica. Sus experimentos con fotones entrelazados sentaron las bases de tecnologías como las redes y computadoras cuánticas y la comunicación cifrada segura, abriendo el camino a lo que hoy conocemos como la segunda revolución cuántica. Es director de investigación emérito del CNRS en el Instituto de Óptica y catedrático, Cátedra Agustín Fresnel, en la Escuela Politécnica de París. A lo largo de su trayectoria ha sido reconocido con algunos de los galardones científicos más prestigiosos, entre ellos la Medalla de Oro del CNRS en 2005, el Premio Wolf de Física en 2010 y la Medalla Albert Einstein en 2012. En 2022 fue galardonado con el Premio Nobel de Física, compartiendo con John Francis Clauser y Anton Zeilinger por sus experimentos pioneros con fotones entrelazados. Es miembro de numerosas academias de ciencias, entre ellas las de Francia, Estados Unidos, Austria, Bélgica y el Reino Unido. Por lo tanto, es un placer y es un honor tener aquí en Teruel a una personalidad tan ilustre como el profesor Alain Aspect, al cual damos la bienvenida. Y quería antes agradecer también al Gobierno de Aragón, al Ayuntamiento de Teruel y la Caja Rural de Teruel por hacer posible, junto con el Cefca, este evento. Muchísimas gracias, profesor Aspect. You are welcome to start the talk. Thank you very much.
Okay. Señora directora, señoras y señores presidentes, subpresidentes, subdirectores, etcétera, etcétera. Estoy encantado con mi visita en Teruel. Muchas gracias al director del Observatorio de Jabalambre, Javier Cenarro, por la invitación a visitar Teruel y para organizar perfectamente la visita con el subdirector Carlos López San Juan. Ayer tuve el placer de visitar el observatorio de Jabalambre y fui impresionado por la magnífica investigación en astrofísica que hay allí. Además, tuve el privilegio de observar el eclipse desde el observatorio. Fue mágico. Hoy tengo la suerte de contar con una sala llena de gente interesada en la física cuántica. Y estoy encantada porque me gusta mucho transmitir mi pasión por las ciencias y compartir la convicción que necesitamos cada vez más ciencia para resolver los problemas del planeta. Lamentablemente, no puedo dar mi conferencia en español. Y voy a pasar en inglés. So I don't know where are the translators, so they are, okay. Translators are ready? Yes, okay, I see. Observing and predicting eclipse is a wonderful model of what is physics. Observing several times surprising phenomena, inventing a mathematical model to describe the already observed phenomena, and using that model to predict new phenomena not yet observed. If these new phenomena predicted by the model are observed, then we know that the model is a good one. This scheme has been successful for more than 1 century with quantum physics, which has allowed us to describe successfully the microscopic world. This is what I will present now. Okay. Now I found to find my gadgets. Okay. Oops. Okay. We don't have the first slide? Voila. Okay. Well, if I move here, you can... Yes, the microphone is working. Okay. So, as you know, I am very happy that my book has been translated in Spanish. And I have a witness that the translation is quite good. It is a professor who wrote the foreword of this book, Ignacio Cirac, who is one of the stars of modern quantum physics. So I'm very glad that he certified that the translation is quite good. Okay. So quantum physics is strange, there is no doubt. But it's absolutely not irrational. What is quantum physics? It's a mathematical formalism, allowing us to perfectly describe observed facts impossible to describe in classical physics. For instance, stability of matter, chemical bonds. Classical physics cannot describe that. Matter-light interaction, and strange things like superconductivity, superfluidity. So as I said first, this mathematical formalism not only allows one to describe this fact, stability of matter, etc., it also allows us to predict new phenomena, for instance, entanglement. This is what I have worked on. Entanglement was in the equations of quantum physics. It had never been observed directly. I went to the lab, designed an experiment to observe it directly, and it worked. It shows that quantum physics is really very powerful. This mathematical formalism also allows one to invent new devices, transistors, lasers, integrated physics. Without quantum physics, you don't have transistors, you don't have computers, you don't have lasers. The problem with quantum physics is that we don't have any simple image to represent the mathematical formalism in our usual space. This is what makes its description difficult and strange if you don't master these mathematics. Anyway, it's the fact that it is strange do not allow you to draw nonsense conclusions. And unfortunately, sorry for the journalists who are in the room, but unfortunately you can read many nonsense things based on quantum mechanics, on allegedly quantum mechanics. So when you read things, be careful. If it is not a scientist who say it, you have to be careful. So there are two concepts for two quantum revolutions. Wave-particle duality for the first quantum revolution with Einstein and Louis de Broglie. And then the second concept is entanglement for the second quantum revolution with Einstein, Podolsky, and Rosen, Schrödinger, John Bell. Let us start with the first quantum revolution. The first quantum revolution is based on the notion of quantization. What means quantization? It means that some quantities can take only some particular, we call it discrete, values, while the classical formalism allows for a continuum of values. And so we say that in quantum physics, the quantities are quantized. For instance, take light. Classically, we describe light as a wave propagating everywhere. So you can take a volume as small as you want of light, and then you have a quantity of light, of energy, which varies with the volume. What Einstein discovered in the beginning of the 20th century is that there are some circumstances where you cannot look at light as some kind of continuous thing. You have to consider it as made of small grains of energy, which have been named photons, okay? And once again, doing this hypothesis to describe some known phenomena, Einstein made some predictions which were checked later by experiments. Of course, there is a problem, because this seems contradictory. It is contradictory, but although it is contradictory, you have to accept that light is both a wave and a particle. This is why I tell you that quantum mechanics is strange, but you have to accept it. And so it is a notion of wave-particle duality. Light is both a wave, which is continuous, and particle, which is discretized. And Einstein made this statement as early as 1909 for light. Quantization is not only for light, it's also for matter. And we will see wave-particle duality for matter. So once again, I repeat, quantization is a fact that some quantities can take only some particular discrete values, while the classical formalism allows for a continuum of values. Take the model of atom that was experimentally observed and built by Ernst Rutherford in 1908. In this model of atom, you have a nucleus with a positive charge and electrons with a negative charge. And these electrons, so to speak, rotate around this nucleus. And because the attraction between the positive charge here and the negative charge here scales as the inverse of the square of the distance, is exactly like the solar system. It's just like a big star, the sun, attracting the planets here. Or it's just like the Earth attracting the satellites evolving around the Earth. But there is a big difference. Satellites can be at any altitude, any elevation. But facts, observation, led Niels Bohr to say that only some orbites are permitted. Only some altitudes are permitted. And so they are quantized. You cannot have any ellipse, any trajectory, only some trajectory are permitted, and it is by jumping from one trajectory to the other one that the atom will absorb or emit light. To understand this fact, that only some trajectories are emitted, there is an hypothesis which was made by Louis de Broglie, and the hypothesis is that because you can think of the electron as a wave, when you think of a wave propagating along the trajectory, after a full turn, the wave had to come back in phase. This means that the length of the trajectory has to be an integer number of wavelengths. And this is the phenomenon that selects the possible trajectories. So quantization is related here again to wave-particle duality. I like very much this slide. Why? Because when I show it to young people, it's just to convince them that quantum mechanics is fun. Look, Louis de Broglie has just found his famous equation, okay? Erwin Schrödinger has just found his famous equation. Look how they are happy. So young people, don't hesitate to do quantum physics. It will make you happy. Okay, now I have a small problem of projection, so you have to listen to me. It's not exactly what you see here. I present here just to show you the kind of experiment we can do in the lab to demonstrate this strange wave-particle duality. This is an experiment that was done by my first PhD student in 1986. We did that together. First, we thought that we were able to emit a single photon, one photon after the other one. Don't think that it is easy. Nobody had done it before us, okay? Being able to say, this is one and only one photon. Now, this is another one and only one photon. And we say if the words have a meaning, when the photon will arrive on a beam splitter here, a beam splitter is just like a piece of glass, okay? If you send a light beam on a piece of glass, a part is reflected and a part is transmitted. But if the word particle has a meaning, a particle will not split in two. It will either go straight or go up. Could we demonstrate that? Yes. Because here we have a detector which detects a photon when the photon comes here. Here we have another detector detecting the photon when it comes here. And we can register the fact that we have a count here or a count here. But here we have a subtle electronic circuit called the coincidence circuit. The coincidence circuit can tell you that there is a detection here and there simultaneously. We never observed any coincidence. This experiment means that the photon either go up or go down. It behaves exactly as a particle, okay? Good, you are going to tell me, yes, of course, a particle goes up or down, not on both sides. Hold on. Then we do a second experiment. And in the second experiment, we same the same single photon. But now we take the point of view that it is a wave. And when you have a wave, when you send it on a beam splitter, the wave is split in two. Okay, so far so good. If we put a detector here and a detector there, it will be detected either here or there. But we don't do that. We recombine the two beams on a second beam splitter. And we observe that the probability of detection here and there depend on the difference between the upper path and the lower path. If what you observe depends on the difference of the two paths, it means that there is something which is split in two and recombined. That calls interference. So in the second experiment, we have the same object, but now this object behaves like a wave which is split in two and recombined. Once again, this is wave-particle duality, okay? And of course, this is very puzzling, but we have to listen a little bit to Niels Bohr, who told us, look, my friend, it's surprising, there is no doubt, but there is something which is sure. You have to choose either this experiment or that one. You cannot do both experiments simultaneously. Try, you will find no solution to do both experiments simultaneously. Which means that, in fact, the behavior of your single photon wave packet, which here, depends on the kind of measurement you do on it. If you try to check that it is a wave, it behaves like a wave. And if you try to check that it is a particle, it behaves like a particle. This Bohr complementarity to make you slightly more comfortable with the notion of wave-particle duality. But I can tell you, I will probably never be fully comfortable with that. Okay. Wave-particle duality is not only a game for physicists, okay? Wave-particle duality already told you, to understand the structure, allows you to understand the structure of matter, to understand its stability. Let me explain you that. At the end of the 19th century, physicists knew that matter is made of positive and negative charges. And they knew that negative and positive charges attract each other. So matter should collapse. Why doesn't it collapse? Because of quantum mechanics. Before quantum mechanics, they could not understand why it doesn't collapse. It does not collapse because the electron, being a wave, cannot crash on the nucleus, because it would demand to have a wave so small that there is not enough energy to make the wave so small. So because there is a finite wavelength, the electron has to avoid crashing on the nucleus. It's just like if a satellite could never crash on Earth. It's only quantum mechanics which allows you to understand that. It's quantum mechanics which allows you to understand the chemical bond. It's quantum mechanics which allows you to understand electrical properties. So it's quantum mechanics which has allowed some physicists to understand how electrons propagate in some materials called semiconductors. And understanding that, they invented transistor. Understanding with quantum mechanics how light is emitted or absorbed by matter, they invented lasers. And this was the key for the society of information and communication. Young people think that we had forever internet, computers, but I see some people in the room who know that before there were not internet, computer, etc. All these results from these inventions, and these inventions were done by the smartest physicists of that time trying to use quantum mechanics. Okay. So the first quantum revolution was first conceptual, with particle duality, scientific, allowing stability of matter, etc., and then technological, inventing such devices which are so important. Let us go to the second quantum revolution, the one in which I have worked. So the second quantum revolution is firstly based on entanglement, and I am going to present what is entanglement. So I will not present it in an abstract way. I will present the experiment we have been doing in my lab in the late 1970s and early 1980s, and the experiment which has granted me the Nobel Prize. We had a source able to emit a photon to the left and a photon to the right. So a pair of photons is emitted. And we are going to do measurement of polarization on these photons. So you are going to tell me you don't know what is, well, some of you may know, but most of you do not know what is polarization. Polarization is a property of matter. When you have a laser beam, like my laser propagating here, in fact, classically, we describe it with an electric field which is vibrating perpendicular to the direction of propagation, which means that it can vibrate in any orientation in a plane perpendicular to the direction of propagation. Measuring this direction is the goal of measuring the polarization. How do we measure the polarization? We measure it with an apparatus here, which is, let's say, a polarizer, which can be oriented. So I have a unit vector A to tell me what is the orientation. And the idea is the following. If the beam is polarized along the axis of the polarizer, the light will go up. If the beam is polarized perpendicular to the axis of the polarizer, which is here, the beam will go down. And if the light is polarized at an angle, a fraction will go up and a fraction will go down. This is classical physics. If now, rather than a light beam, I have a single photon, the photon will not be split in two. It will go either up or down. Once again, quantization. You can get only result +1 or result -1. Now, what happens? If the photon is polarized in this direction, it will go up. If the photon is perpendicular to this direction, it will go down. And if it is polarized in a kind of intermediate state, sometime it will go up, and sometime it will go down. And so you have to repeat the experiment and do statistics and determine probabilities. What is the probability to find it up, and what is the probability to find it down? And the mathematical formalism of quantum mechanics is exactly the formalism that allows you to calculate the probabilities. So you can do a calculation, say in this situation, this is the probability of +1, this is the probability of -1, and you can compare to an experiment if you repeat the experiment often. Okay? Now, don't be afraid. You are going to see that you can know much more than you thought. Here, I explain what is an entangled state, but rather than explaining, I show the formula showing what is an entangled state, and now you are going to see that it is really strange. You see here I have axes, x, y. Here, this strange term, xx, means that I have two photons which are polarized along x. Simple to understand. The second term here means that I have two photons which are polarized along Y. Simple to imagine. Now, what Einstein, Podolsky, and Rosen discovered in 1935 is that you can form a state like that, which is the fact that if XX is allowed, if YY is allowed, then XX plus YY is allowed also. And then you are in trouble, because you cannot make an image of something which is both this and that. You can try, you will never succeed in saying, oh, it's one photon rotating like that, another one rotating like that. You have to continue saying it's both this and that. And in a sense, it's as strange as the Schrödinger cat, which is both dead and alive. You have to admit the superposition of two things which look totally incompatible. Okay. So Einstein, Podolsky, and Rosen discover that state and say, look, if this state really exists, and when you look at the mathematical formalism of quantum mechanics, the mathematics tell you it is possible, then you say, we can calculate the probabilities to get +1 and -1 on such a state. You do the calculation, it's a calculation not very difficult, well, provided that you have studied a little bit of physics. You do the calculation, and you find the probability of getting +1 and -1 are equal to 1/2, 50%, whatever the orientation of the polarizer which is here. Same thing on the other side. So it looks totally uninteresting. Here, you have +1 and -1 at random. There, you have +1 and -1 at random. Doesn't seem really interesting. But when you calculate the probability to get +1 here and +1 here, you look at both results, okay? It's called the joint measurement. When the polarizers are along the same direction, if you calculate the probability to get +1 and +1, you get 1/2. Well, okay, why not? Then you calculate -1, -1, you get also 1/2. And then it means that the probability to get +1, -1 is 0. In other words, this calculation tells you the probability to get +1 or -1 here is 50%. The probability here is 50%, but if you get +1 on one side, you are sure to find +1 on the other side. And if you find -1 on one side, you are sure to find -1 on the other side. This is what we call a total correlation. I like to call it a tricky coin toss for the following reason. Suppose you have somebody here throwing a coin. The result looks totally random. And on the other side, you have another person. We call them Alice and Bob, okay, in quantum physics. So Bob is also throwing a coin, and you can check it looks totally random. But people who are in the middle will be surprised to observe that when Alice gets +1, then Bob gets +1, and when Alice gets -1, then Bob gets -1. There should be a trick, okay? There is no magic in physics. There should be a trick. We are coming back to this trick in a moment. So, as I told you, the idea of physics is to try to describe surprising phenomena. So here we have this surprising phenomena of full correlation between both ends. Do we have a mathematical formalism for describing it? The answer is yes. I have a calculation predicting that, okay? But now, can we make an image for that? I am a naive physicist. I like to have images. Can we make images for that? And usually, when you are a physicist, you have a calculation, you look at the calculation, and you can develop an image and say, oh, now I understand. Here, it's not possible. The reason is that the calculation that you do for calculating these results is done in an abstract space where you describe simultaneously the two particles, and it's not easy to come back to the space where we live. In the abstract mathematical space, no difficulty. But in our space, it's difficult. I will come back to this point at the end of the talk. Okay. So, you cannot find easily a description in our space. But on the other hand, as a famous theorist for quantum optics say, quantum phenomena do not occur in a Hilbert space. A Hilbert space is an abstract space. They occur in a laboratory. And in my laboratory, there was a source in the middle, a polarizer here, a polarizer on the other side. I want to understand what happens after the moment when the two photons are emitted and arrive on the polarizer. I want an image in our space. In fact, there is a possibility for doing that. And this possibility was suggested by Einstein, Podolsky, and Rosen in their paper in 1935. And we will come back to the trick for the tricky coins. The idea is the following. The two photons are emitted by the same source. So we can think that from the beginning, they have a property which is the same for the two photons, which from the beginning decide that the two photons will go up. And then for the next pair of photons, there is a property which from the beginning decide it will go down. Let us come back to the experiment with Alice and Bob throwing coins. In fact, I did not tell you everything. In fact, there is a machine in the center, okay, because I want to mimic that. And the machine sends a coin to Alice and a coin to Bob, okay? And now they do that. And what can be the trick? The trick can be that the machine sends coins with two heads. The same for Alice and the same for Bob. So they throw head, head, ha. Next pair is two head and tails. Is two tails, okay, etc. That's exactly the idea that you have here. When the two photons are emitted, they have the property that decides from the beginning that you will get +1, or -1. Sounds a wonderful idea, and Einstein loved it because he did not like the idea of probability, so he preferred the idea that it was determined from the beginning. But Bohr did not like it at all for the following reason. If you accept this idea, you introduce a parameter lambda which comes in addition to the mathematics of quantum physics. And Bohr had the intuition, I say had the intuition, he did not demonstrate it. Bohr had the intuition that the formalism of quantum mechanics is complete. You cannot add anything to it. So you cannot add supplementary parameters. Okay, so this was a debate between Einstein and Bohr in 1935. Okay. What happened? Nothing. Bohr and Einstein continued to argue on this problem until their death, and basically nobody cared. The other physicists did not care. Why? There are many reasons why they did not care. First, they were using quantum mechanics every day in their lab to describe phenomena, and it was working. So obviously, it was a very nice theory. Second, this, as I told you, these quantum mechanics allow them to predict and observe new phenomena, to make inventions. But I think the main reason is the following. At this stage, the discussion or the disagreement between Bohr and Einstein was philosophical in nature. It was about the way to describe the world. There was no disagreement on the result of the calculation. And so you have Einstein and Bohr who make the same prediction, and you observe in your lab that it works. You don't go further. You say, okay, they have different model in their head, different epistemological model, but this, maybe I will think about it when I retire, okay? But today I don't have time enough. I have to go to my lab, I have to teach my student, I have to write a paper, okay. And so I think that this is the main reason why nobody cared, because it sounded to be only a philosophical question. The situation changed in 1965 when John Bell, a theorist in CERN in Geneva, discovered that if you take seriously the point of view of Einstein, in some very rare situation, you come to a conclusion different from the standard conclusion of quantum mechanics. In other words, now you have two points of view leading to different predictions. So if you are a reasonable physicist, you go to the laboratory and you look into that situation. This situation was so rare that nobody had yet explored it. And this is why it was necessary to build new experiments to settle the debate by testing what is called Bell's inequality. Bell's inequality means that if Einstein is right, some quantity is less than 2, and if Bohr is right, this quantity is bigger than 2. And so this is what you have to do. The first to do an experiment like that was John Clauser. You see young John Clauser in 1972 in his lab with his big apparatus, etc., etc. So in fact, the situation was interesting because there were 4 experiments between 1932 and 1972 and 76. One in Berkeley, one in Harvard. You know, Berkeley, Harvard, a big competition between the East Coast and the West Coast. Berkeley and Clauser found quantum mechanics, Bohr. In Harvard, Frey and Holt found Einstein. Okay. And then there was another experiment in Texas. And after these 4 experiments, the score, you know, like in the soccer game, okay, oh, he should not mention that here, okay? I am French. So like in soccer games, the score was 3 for quantum mechanics and 1 for Einstein model. Anyway, these experiments were very different from the ones I have described previously. And so this is why I embarked into a new series of experiments to have experiments much closer to the real debate between Einstein and Bohr. And so this is the experiment I built. It was 10 years after Clauser when I got my result in 1982. And in my experiment, what I could do that Clauser had not done is 2 things. The first one is I could obtain real polarizing splitters. In the theoretical drawings, we drew that, but nobody had it. I was the first one to have this, and I could do an experiment extremely convincing, showing that there is no doubt you violate Bell's inequality by a huge effect. But the most new experiment, the one which granted me a Nobel Prize, is the following. Bell had told us that what would be really interesting would be to change the orientation of the polarizer while the photons are propagating. And so you have to remember that, or if you look at this, between my source and my polarizer, there is 6 meters. To travel 6 meters, light takes 20 nanoseconds. A nanosecond is a billionth of a second, okay? So it's quite fast, huh? And so you want to change the orientation of a polarizer in less than 20 nanoseconds. And this is not possible because the polarizer is a big object, a big device. So I got the idea of having a trick. If I could build a switch, either letting light go in this direction in a first polarizer oriented in one direction, or sending the photon in another direction with a polarizer in another orientation, if the switch is fast enough, then this is equivalent to a polarizer switch from one orientation to the next one. This is what I did, building such a switch and doing the experiment. Okay? Yep. Voilà. And, okay. And in all these experiments, I found agreement with quantum mechanics and disagreement with the model of Einstein. Okay. My experiment was much better than the one of Clauser, but it was far from perfect. So there have been new experiments in the next decade. The reason why my experiment was possible is because I built a source of entangled photon much better than the one of Clauser. And then in the new generation of experiments, they built new sources of entangled photon much better than my source of entangled photon. This is how science makes progress. Each generation builds some new equipment, apparatus, new ideas, etc., and then you make a progress, okay? And then with these sources, what was good with their source is not so much the number of entangled photons per second. It was the fact that the photons were emitted in well-defined direction. In my source, photons were emitted in any direction in space, so I had to use big lenses to collect them, etc. In the new source, the photons were emitted in a well-defined direction, so well-defined that they could inject the photon into optical fibers. And if you can inject them into optical fiber, then you know you can have a long distance. So you have plenty of time to do interesting things. For instance, Zeilinger repeated my experiment, but he had time to rotate the polarizer, or equivalent of polarizer, and he had enough time to run a random number generator. So he was choosing the orientation randomly, with a decision taken randomly here. I could not do that. What I could do was switching like a crazy. That was all. Zeilinger had enough time to throw a dice, so to speak, it was an electronic dice, and to repeat the experiment. He found the same thing as we found. Okay. And there were many other experiments, okay? Nicolas Gisin did in the same year, in 1998, in the same year as this one, he did an experiment that I liked very much. He demonstrated that you can propagate entangled photon on a commercial network of optical fibers. So he injected a pair of entangled photon here in Cornavin. He had a detection in Bellevue, and he had a detection in Bernex. You have more than 10 kilometers, okay, between the two sites. And he still found quantum mechanics and not Einstein, etc. So entanglement was surviving such a long distance. Nowadays, in application, they do that in commercial networks on much longer distance. Okay. And then there have been a full series of, because every time somebody was saying, yes, but your experiment is nice, but there is still a small problem here. So each time somebody was building a slightly better experiment, and eventually in 2015, 3 experiments were presented, one in Vienna, one in Boulder in the US, and one in Delft. And the 3 experiments were claimed to be loophole-free. So there were no more discussion. Well, in fact, there is always a possibility to argue. But basically, there was an agreement. There were definitive experiments. And the conclusion was that you have to reject the point of view of Einstein, the description of the world that Einstein was giving us. What can we do with that? I am going to tell you. So we have to abandon the point of view of Einstein. What should we conclude? Well, in fact, we have just to read Einstein. Einstein told us what we must conclude. So you may be surprised. You say, oh, Einstein was not believing in what he was claiming? No. He was doing a reasoning ad absurdum. He was telling, if I was not right, this would be the unbelievable thing you should have to believe. But now we know that we have to believe these things. So these are the words of Einstein. If I was not right, you would have either to abandon, I will explain the words, okay? Either abandon the independence of the physical reality present in distance volumes, or accept that the measurement on one system modifies instantaneously the real situation of the other one. What does it mean? It means that I have 2 particles. They propagate. They are well separated, well localized in space-time. Okay, I can think of the photon in a given volume that is propagating like that. Then the local realist vision of Einstein was that as soon as you have something like that, which is well isolated in space-time, there is a number of parameters which describe the physical reality of the system, which means that whatever measurement I do here, I can calculate the result with these parameters. And for the other particle which is there, same thing. There is a physical reality, and this physical reality determines the result of measurement. Well, we have to abandon this idea. Even when the two particles are separated, we cannot think separately of a physical reality of the first one and of the physical reality of the second one. We have to think of it globally, although they are separated. Another way of expressing that is to accept that when I do something with the first particle, in some sense, it changes something on the other one. This is called non-locality. So the first point of view is called quantum holism. Holism means the two particles are a whole, you cannot separate them. And the second point of view, which is kind of equivalent, is to say, okay, when I touch the first one, it changes something on the other one. So this is the conclusion that we have. Okay. What can we do with that? Well, some smart people have found ideas for exploiting that. So we are now going to talk of something precise, which is something I like, which is the notion of non-locality. Not everybody agrees with me, but I like the idea of non-locality. And it is one chapter in the book which is translated in Spanish that probably somebody will offer to sell here. I don't know. There will be some selling of books. I don't know. But you can order it if you want. Okay. So I will develop this idea of non-locality to let you understand how it can have an application. Let us come back to the idea of non-locality. I come back to the experiment I described at the beginning. The photon arrives here, it can be either +1 or -1. The other arrives, it can be either +1 or -1. But there is one way to describe the situation in our space, and that way is the following. You say, okay, let's suppose I have the result +1. What does quantum mechanics tells me? It tells me that just after the measurement, then the pair of photons is no longer described by this state, is described by that state. And what is that state? It's just two photons polarized along X. So if I find a polarization along X, then the second one is polarized along X. Now I understand why it is +1, +1. And I can do the same reasoning for -1. If I find -1 here, then it will be Y. And then instantaneously, the other photon will be Y. This is non-locality. And if you accept this non-locality, you can make, between quotes, sense of the fact that the results are fully correlated. So it's an image which is in real space, which yields the same result as the full calculation in the abstract mathematical space. So I am happy. I have an image in our real space, a space where we live. But look at what it tells you. It tells you that until the last moment of the measurement, it can be either +1 or -1. But as soon as you get the result, instantaneously the other one knows that it has to be +1 or -1. This is what my experiment demonstrated, because in my experiment, since I was choosing the orientation at the very last moment, it showed that the process was happening at the last moment and not before. Okay, so obviously, this was not along the idea of Einstein, but we have to accept it. And now I am going to show you how accepting the idea of non-locality gives me intuition about one beautiful quantum technology, which is called quantum cryptography. This is the idea of cryptography. You have two friends, the famous Alice and Bob, okay? They want to exchange a secret message, and you have the spy, the eavesdropper, which is here, and the eavesdropper wants to intercept the message. What can they do? At this stage, there is no quantum physics, okay? What can they do? Shannon, in 1947, demonstrated, Shannon was a fantastic mathematician who invented the theory of information. He showed that there is a method which is absolutely secure. It's called one-time pad. In this method, Alice and Bob have an identical random series of 1 and 0, okay, exactly the same. So Alice uses this to code her message. She sent the coded message, and Bob uses the same series to decode, and that works. That works under one condition. It is that the message must not be longer than the series that you have here. Because if it is longer, somebody who intercepts the message will observe some regularities. Maybe you have looked into novels or even history books showing how you can crack codes because, there are repetition and things like that. So in order to have this method absolutely safe, you need to have a very long series of random 1 and 0, and the same one here. So how do you do to give to Alice and Bob a similar random series of 1 and 0? Entangled photons. So, once again, you have here the source. This is a modern source of entangled photon. You send your 2 photons here, and then if Alice and Bob have chosen the same direction for their polarizers, if Alice gets +1, Bob gets +1. And if Alice gets -1, Bob gets -1, they can decide that it is 0. And this is how you distribute to Alice and Bob exactly the same series of random numbers here and there. Where is non-locality in that? It is in the fact that before the photon arrives here, the decision is not yet made. So there is nothing to spy for the spy here. If the spy tries to spy, he fails because of non-locality. It is only at the last moment that it will be decided that it is +1 or -1. So this is a reason why I like quantum non-locality, because it allows me to explain simply how this method of quantum cryptography works. Otherwise, I have to make very complicated calculations to convince you, and of course, I am not going to convince you. Okay. Just to mention, Chinese, Jian Weipan, have played by putting a source of entangled photon in a satellite. They send it to 2 detection stations, which are more than 1,000 kilometers from each other, and they have found the joint detection, and they have distributed random keys for coding and decoding information. So, this application now exists. Okay. So what do we do? I'm going to observe from back again what is the second quantum revolution. The second quantum revolution is based first on entanglement. You remember the first one was based on wave-particle duality. Wave-particle duality was for single particles. Entanglement is for pairs of particles. And so it's an amazing property, as guessed by Einstein. Bohr immediately realized that it was serious. Schrödinger realized that it was fantastic, and other physicists did not care. Okay, well, but eventually, for instance, Feynman. It took him long until he realized. For people who have learned physics, they know that Feynman wrote a fantastic book in 1960. In his book in 1960, he said, discussion between Einstein, Podolsky, and Rosen, nothing new. But 20 years later, in 1982, Feynman said, maybe I was wrong. Maybe it's interesting, this question of entanglement. And Feynman, being Feynman, as soon as he realized that entanglement is interesting, he invented the first concepts of quantum computing. Okay. So, entanglement, there is no doubt that it is important. But there is another property that we should not underestimate, which is the fact that starting in 1970, experimental physicists became able to observe, manipulate, measure single quantum objects. Before 1970, nobody had ever been able to make measurement on a single quantum object. It started with an electron, which was trapped in magnetic and electric fields by Mr. Demelt in 1970. Then people were able to manipulate single atoms, were able to produce single photons, etc., etc. And so the second quantum revolution is a combination of understanding and trying to put in action entanglement, and you do that by manipulating single objects, taking them, entangling them, separating them, etc., etc. So when you read the news about quantum computer, it's all about what kind of object am I able to manipulate. You can have photons, you can have atoms, you can have superconducting circuits. The Nobel Prize 2025 was given to people who have demonstrated that some superconducting circuit can behave as elementary quantum objects, and so you can entangle them. And so the fight for the quantum computer is a fight for trying to find what is the most successful kind of quantum object that you can manipulate and entangle. Okay, so what can we do with that? Well, three kinds of application. Quantum communication, I already mentioned it, quantum cryptography. Teleportation, don't be fooled with the word teleportation. This is a joke of physicists, okay? Because as soon as you hear of teleportation, you say, okay, I push on a button and I go from here to there. No. Teleportation for a physicist is as fantastic as that, is the fact that I can take the mathematical description of the object which is here, it's called the quantum state, and send it to another quantum object which is there. You're going to tell me why it is useful. It is useful because if here you have a first quantum computer whose output is given as a quantum state, and if you need to use that quantum state for a second quantum computer, it's crucial to be able to transport it without spoiling it. This is the idea of quantum teleportation. Okay. For us, it's extremely important. Quantum computing, I already mentioned it. You have here ions, here atoms, here superconducting, etc., etc. And quantum metrology, the fact that you can manipulate single quantum object allows you to make measurements that you could not do before. Okay. Now, what will happen with that? Okay. Will the new quantum revolution have a major impact on society? You can hear about quantum advantage. Quantum advantage, when you read it in the newspaper, and most of the people who talk about it will tell you, oh, if we have a good quantum computer, it will be able to make calculation you cannot do with a classical computer. This is true, but there is another point of view. It might be that a quantum computer allows you to make a calculation that you could do with a classical computer, but with much less energy. This would be also quantum advantage, because you know that these big computers take more and more energy. So, will it work? Well, states believe in it. Europe puts money. France puts money. Spain puts money. All the states put money in this research. Big company, IBM, Google, Microsoft, Amazon, Bull in France, put money in the development of quantum computer. We don't know if it will work or not. You have plenty of startups here also, which try to bring their stone to the development of quantum computing. We don't know if it will be as fantastic as we hope, but it's a fascinating perspective, and I tell young people, if you are interested, don't hesitate to go there. And maybe I have something to show to finish. Yes. I need to say that when I did my experiment in 1982, I had two young students who just joined my group for their master degree, okay? Not more than that. And they were fantastic students. And these fantastic students have become celebrated physicists. Now they earn, well, we are going to give a prize with the European Physical Society to that one. This one has also accumulated many prizes. And for this reason, they were with me in Stockholm to receive the Nobel Prize in 2022. Thank you very much. Thank you.
I think it's time for questions. Is there any questions in the audience? Somebody wants to ask something? o en español, si queréis preguntar en español, también podéis.
Okay, don't hesitate.
¿Queréis ir primero? Vale. ¿Ya está encendido?
Sí.
Professor, thank you very much. It was a very enlightening presentation. I really enjoyed it. I did not quite understand how this source works. Because it seems to me like you are forcing them to become +1 or -1 -1.
No.
Okay.
I force them to be XX plus YY. Okay. If I was forcing them to become either +1 or -1, I would not find the violation of Bell's inequality. This is the point. So, in a sense, I could tell you it's my business to do the source, but I can explain you how I do it. But the fact that I violate Bell's inequality means that my source doesn't emit +1 or -1. It emits the superposition of +1 and -1. So I send a file. I may have here something to explain. Do I have something to explain how the source works? Okay. I think I have here. No. Voilà. If you know a little bit of physics, this explains how my source works. I have an atom of calcium. I have several atoms, but let us concentrate on one of these atoms, which is in a vacuum chamber. By shooting two lasers on it, very well tuned, very precisely tuned, I can excite one level. And when the atom is in this level, it has no choice. It can only decay, sending two photons, a green one and a blue one. Okay, so it's my two photons. But now, if I go into details, it turns out that this level, in fact, can be decomposed in two levels. So in fact, when this process will happen, it can be either through this level or through that level. And in quantum mechanics, there is a basic principle. When you have two paths, if you cannot distinguish between the two paths, you have to add the amplitude. So in fact, what you produce is a superposition, which at the end is a superposition we make. So this is my way of doing it. But in another sense, I could hide it and not tell you. Because the important thing is that at the end, I do violate Bell's inequalities.
Thank you very much.
Pleasure.
Hello. Thank you very much for your talk. It was very enlightening. It's only a stupid question, but if your experiments took place in the 80s, why were you granted with the Nobel Prize in 2022, I think?
So you want that I try an explanation?
Yeah, maybe it's only because of that, because it took you 40 years to get
I could tell you that Michel Devoré, John Clark, and John Martinis got the Nobel Prize 2025 for experiment done in 80-85.
Okay.
So it took 40 years for them also. But it's not the only reason. I can go into tell you a few things. When I started in 1975, most of the people were telling me, but this is absolutely not interesting. Everybody knows that Bohr is right, etc., etc. And it is by doing this experiment that progressively I attracted the attention of people saying, look, maybe that Bohr is right, but entanglement is really extraordinary. And at the end of these, people realize that it is extraordinary, and some smart people, as I said, Feynman, for instance, and another one say, oh, but if entanglement is so extraordinary, then we can do something with it. And so, you know, there was this process, first saying, well, this is crackpot physics, and then this is uninteresting physics, and then, oh, it's interesting, and then somebody, we are going to use it. And it has taken many decades until we have real application. And the reason, in my opinion, why they gave it to us in 22 is because now there are serious applications, quantum cryptography, quantum metrology, and the progress of quantum computers. Quantum computers are not yet full-fledged, but they are in progress. So they thought it was a time for that, and it's probably the same reason why they give it to Michel de Voré, etc., for superconducting circuits. So, you know, there are so many people who could get a Nobel Prize. They have a difficult choice. So you need to have some... I think that really the fact that we speak more and more about quantum technologies with demonstration was the cherry on the cake who say, okay, it's time to give to them. There was no doubt that it was interesting. But, you know, there are so many interesting things who never get a Nobel Prize.
Yeah, so my question was more than what changed. Nothing. That people were convinced about it.
What changed is first people realized that it was interesting, and second, that this interesting thing was leading to applications.
Okay, thank you very much.
More questions? There in the... Okay, sorry, yeah.
Yeah, thank you, Professor, for your talk. I just wanted to ask about a comment that was like here down. In the experiment, if the distance is long enough and the, you know, like a speed of light is slower than the information that is transmitted,
yes,
there is a problem. Yeah.
Yes, of course there is a problem. If there was not a problem, nobody would have been interested. So it seems that something is going faster than light. It's the idea of non-locality. But you can demonstrate that that thing does not allow you to send useful information faster than light. And I can demonstrate it. I saw that I have the slide here, so I will show you that. Toc, 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 toc. Boom. Voilà. Voilà, voilà. So it's not possible to signal. Signal means I push on a button and then there is a light which leads here, okay, which is on here. You cannot do that faster than light, in spite of non-locality. Why? Let us think that Alice, which is here, is trying to send an information to Bob by suddenly changing the orientation of her polarizer here. So the photon, which is here, immediately changes. So can Bob know that it has changed? No, because it's a single quantum object. And a single quantum object, when it arrives here, it will randomly give +1 or -1. So if Bob looks only at its photon, he gets +1 or -1, and nothing changes in his statistics. What changes is the correlation between Alice and Bob. So if Bob compares his result to the result of Alice, then he can know that something has been faster than light. But to make the comparison, Alice has to send him a message by a classical channel. And a classical channel cannot go faster than light. And this is something which happens in all the schemes of quantum transmission, quantum information. You always have a quantum channel. In teleportation, the same. You always have a quantum channel that you describe as instantaneous, and a classical channel in which it has to go with the speed of light. Okay? So you are going to tell me it's not interesting. Yes, it is interesting, because by looking at this, in the case, I cannot do that, but you seem to understand a little bit of physics. In the case of quantum teleportation, this tells you that because there is something instantaneous affecting the photon which is here, but something which takes time, I need a quantum memory here to store the photon, to wait for the classical signal arriving. So my claim is the following. The notion of quantum non-locality is useful to make hand-waving images. So this is my way of doing physics. I have intuitions based on images, and when this intuition tells me this should be interesting, then I do the full calculations, everybody. We all agree on calculation. We disagree on images. My favorite image is non-locality. Many people do not like non-locality. Doesn't matter. We all do the same calculation, and we agree on the result of the calculation. I explain that in the book. No, seriously.
Lo primero, muchas gracias por la charla y mi pregunta...
Either you speak slowly in Spanish and maybe I understand,
Okay.
or somebody will have to translate.
Ok. Muchas gracias por la charla y mi pregunta es, ¿usted cree que las computadoras cuánticas pueden descifrar los bitcoins?
I'm not sure that bitcoins is so important. The important point, I have no idea. You know, it's a very specialized thing, and who knows? No, the important thing at the moment is, will the quantum computer work as well as we think they should work when we do calculation? Because there are terrible, difficult technological points to solve. And so once we solve these points, then we are going to show how we can use a quantum computer. In fact, we can already use imperfect quantum computer to make some calculation, for instance, useful to screen drugs, okay, molecules that could be used for drugs or things like that. And so, you know, science is not something where suddenly, yesterday it was not possible, and tomorrow everything is possible. Science is one step after the other one. And every other year, quantum computers are better. And we don't know yet what will be possible to do with quantum computer because it depends on the progress we are going to do next year. But, you know, I'm not sure that Bitcoin is such an interesting subject. I'm sorry to disappoint you.
Muchas gracias.
De nada.
More questions?
Hello. The first thing I want to say is that congratulations for the talk. It was amazing. I really loved it. And I studied physics. I think you make it really easy to understand it for someone that has already studied some quantum physics. And my question is regards what I think is a big problem today in science, which is data transfer. No, in science, especially, for example, someone that works in interferometry, radio observations, sometimes it's even faster to ship your data, no, the data you just observe in a plane to your location rather than just sending it over the net, no? Or from downloading from an archive. So, I don't know about theory information. I studied this just 4 years ago during my master, but we didn't enter in theory information. So maybe what I'm about to say is impossible, but with all these advances in quantum computing, quantum cryptography,
quantum
information, could it be not instantaneous because we just saw it, but maybe it could make really much faster the data transfer between point A and point B, which is today a kind of a big problem?
The question is not so much to be faster. The question is, in principle, quantum computer, quantum register can accumulate a quantity of information that we cannot even think of because it's going exponentially with enough of quantum bits. I am going to try to explain that. If I have 2 entangled qubits, a qubit can be 1 or 0. If I have 2 entangled qubits, the mathematical space, the Hilbert space, in which I describe it, has dimension 4, because the basis can be 0, 0, 0, 1, 1, 0, or 1, 1. If I take 3 qubits, the space where I describe my state has dimension 8. If I have 10 qubits entangled, the space where I describe it is already dimension 1,000. If I have 20 entangled qubits, the dimension is 1 million, etc., etc. If I have 100 entangled qubits, perfect, okay? 100 perfect entangled qubits, the quantity of information I can put in that is absolutely unbelievable. And this, the basic idea for the power of quantum computing. So what you put your finger in is that the fact that with entangled qubit, you can put in between quote, a simple system, a huge quantity of information. Then I could argue that you can do the same thing if you transmit entangled qubit, etc. But I prefer to concentrate on that because it's a basic idea beyond quantum computing. The basic idea is that this huge quantity of information in only 100 qubits can be transformed, and it's called massive parallelism. So that's the basic idea. I see that the translator is doing the same gesture as me, and it's really impressive. When I do that, he does that also.
That is really interesting. Thank you very much.
More questions? There, Javier.
Gracias, profesor. Quisiera preguntarle si de los grupos de trabajo que ahora mismo están desarrollando diferentes tecnologías para fabricar qubits, ¿por cuál apostaría usted?
I've not understood the last point.
Which would be your preference?
My preference is just the one that I understand better, which is neutral atoms. Moreover, because it has been developed by my former students, they have attracted me to come with them in a startup which is working on that. So it is my preferred, but I don't say it is the best. It is my preferred, first because I am involved in it with fantastic students and I'm collaborating with them, and second because I understand it better than the other technologies. But nobody knows who will win. But there is something which is sure, is that people have to exchange information. And when something is better on one side, maybe the people on the other side can try to take advantage of that. It's very likely that at the end, we will have hybrid system. For instance, we will have system with neutral atoms and photons, for instance. So my preference is not the important point. If you want to invest money on it, the best advice I can give is put an equal amount of money on each of them.
Yes, here.
Thank you so much. You mentioned earlier quantum metrology. I had a question. Have we seen the impact on quantum physics on commercial instrumentation yet? Have we seen new detectors or the like?
Yes, you have. Well, it's not big companies, but you have startups which are developing apparatus. For instance, you have some individual quantum objects which are called NV centers. You can put it's some kind of artificial atoms, okay, little crystal of diamond, which is like an artificial diamond. You can put that, its dimension is a few nanometer. You put it on a point, on a fiber, something like that, and then you can explore a magnetic field at the scale of the nanometer. And yes, you have apparatus like that. It's not yet something which is widely used, but the answer is yes, it works.
Thank you.
And there are some people who, for instance, think about using this kind of technology for measuring the signals of your heart or of your brain, okay? Because you can go really very close to the place where the signals are emitted. Because the smaller, once again, remember, the second quantum revolution is individual quantum object. And if your quantum object has the size of a few nanometer, it means that you can go at a few nanometer from the signal you want to measure. So my answer is yes, it already works. Well, there is an application which really works, and you can buy an apparatus. It is an apparatus, former students of mine again, it's an apparatus where you measure gravity by doing quantum interference between falling atoms. And the apparatus, probably there was a slide here, is that big. The weight is 60 kilograms, and it's as good for measuring gravitation as previous pieces of equipment, we were 1 cubic meter and 1 ton. And these apparatus work well enough that they put some of them on some volcanoes, for instance, Etna or this kind, okay? And the hope is to be able, by measuring the fluctuation of gravitation, to predict that there is going to be a volcanic eruption. So this kind of apparatus is already bought by people doing geophysics and these kind of things. So yes, there are applications. It's not a market of billions, but it does exist.
Hi, thanks for the for la charla. I would like to ask that the quantum computers you have mentioned have the problem that interference difficult the read of the qubits, and it seems to beneath the almost absolute zero temperature.
No.
But you seem to have avoided these problems.
No.
What the difference between them and your experiment, and how the entrelazamiento could help?
Okay, it depends. If you work with superconducting circuits, you have to go very close to absolute zero. But, for instance, neutral atoms are held by laser in a vacuum chamber, which is at room temperature. But there is a vacuum, so there is no contact between the walls of the vacuum chamber and the atoms. So all the point is that if your lasers have no fluctuation, then the atoms which are held by the atom are at so-called absolute zero. But you don't have any refrigerator. I mean, it depends on the technology. But for neutral atom, this is not a problem. For superconducting circuit, it's definitely a problem. But every solution has its own problems and solutions and advantage and disadvantage. And this is why we don't yet know the end of the story.
Oh, thanks.
Muchas gracias, profesor. A mí me gustaría preguntarte si tuviéramos, por ejemplo, dos partículas entrelazadas y una de estas se encontrara en un espacio distinto como en una singularidad dentro de un agujero negro, si supondría algún problema para que pudiera darse este fenómeno.
Can you translate for me?
So in case that there are two particles entangled, and one of them were located in a singularity, like for instance, in a black hole, how would that work? Would that be possible?
You have to ask theorists. I understand theory, but this kind of theory, it's almost science fiction. Okay, it's close to science fiction. So, no, it's not really science fiction. For instance, Stephen Hawking made a calculation saying when I have a pair of entangled particles, one is in the black hole and the other one is outside, and there is a complicated calculation, complicated conclusion. If you want to know the answer to this question, you have to ask not to me. And no, I'm sorry, it's an extremely difficult theory. So you can ask Roger Penrose or people of that kind. You should invite Roger Penrose. He can ask the question. No, I am sorry, but I could just say simple things which probably are not relevant. So I don't know.
Hi.
Last question, because I think we are running out of time.
Okay, thank you.
Yes.
Thanks for your amazing talk, Professor. My question is, if you think that quantum physics is already mostly complete, or is there still any big front that might be revolutionized soon?
If I knew, I would not tell you. But what I can tell you is that any reasonable physicist thinks that every theory will arrive at one point on a limit. Here, the hope was that with entangled particle and this question of testing Bell's inequality, maybe we could find a small place where we have a problem. Because progress in physical theories does not mean that you abandon the former theory. It means that It's good almost everywhere, except in a small zone, and so you have to find a bigger theory which includes the first and the second zone. The best example is mechanics. Newtonian mechanics is perfect for calculating eclipse, motion of planets, etc. But when an object is going at a velocity close to the velocity of light, you need relativity. But classical mechanics is included in relativity. So I hope that we will find a limit of quantum physics and that we will have a bigger theory, including what is sure is that quantum physics, as we know, will survive. But maybe it will be included in a bigger one. That's my hope.
Thank you very much. So thank you very much. We are running out of time and we have to start the questions. Thank you very much for coming. Thank you very much for the interest and the questions that you have presented. Just a couple of announcements. Now, Professor Aspect is going to be willing to sign books. Okay, so if you have your own book, then we are going to sorry? Okay. Are you translating or yes? No, I continue in English. So if somebody wants to sign the book, Professor Aspect is going to be here. And if somebody wants to buy the book, it's outside. There is a bookstore. Well, the bookstore is there, okay, selling the book of Professor Aspect. And with this, I would like to thank very much. It's been an honor having Professor Aspect here in Teruel. And we are very delighted to have here his talk. And I would like to thank, with a big applause, to Professor Aspect.
It's a pleasure for me to have such a beautiful public. Merci.